Okay, let's work on another coding exercise. So we're given an integer array of numbers, and we want to return the largest perimeter of a triangle with non-zero area formed from 3 of these lengths. And if it's impossible to do so, then return 0. So basically we're given some numbers and we try to form triangles with lengths equal to like 3 of the side lengths in this array. And so there's a couple things we need to think of. First of all, we need to remember what is the correct condition for knowing when 3 numbers can form a triangle. So let A, B, C be integers, and 3 of these lengths. Yeah, so, it does say. So like each of these values is going to be at least 1. So no dealing with like what does it mean to have a negative length. The integers which are greater than 0 or greater than or equal to 1. Now, okay, so let's assume, without loss of generality, that A is less than or equal to B is less than or equal to C. Because we could just rename the 3 integers to make sure that this is going to be the case. Okay, so given 3 integer values, 3 positive integers, with C being the largest, when can we form a triangle whose side lengths are equal to these 3? And so basically, like if you remember the triangle inequality, a given vectors u and v, the norm of u plus v is less than or equal to the norm of u plus the norm of v. It's basically this. So basically what it ends up being is that we need to make sure that the lengths of the 2 smaller sides is greater than the length of the longest side. And I guess this is sort of like a backwards way to explain it, because typically what you would do is you would start with the more like, because this is more of like a geometric statement, and this is more of a statement about vectors. So you typically like when you're learning, you start from this and then you eventually build up to this. So the way I've presented it is a little bit backwards, but it's just sort of like, if you have mathematical training, then you work with the triangle inequality so much that it's sort of like baked into your head, so much so that this becomes more natural. Like you think about this more than you think about the simpler interpretation. But anyways, yeah, so if you're comfortable, like you know this and you can move forward, that's fine. I'll take a moment just to like prove this and like validate that this is the case. And I'm going to do this geometrically. So I'm going to try to draw a straightish line. That's actually pretty good. Well, actually, I want it to be a little bit shorter. Oh well. So we'll say that we have a triangle, and we'll have like points P and Q. And we'll suppose that this is a line segment of length C. Okay. So then we want to figure out if we can create a triangle whose where the other 2 side lengths are equal to A and B. Okay, so let's just take let's take smaller values for an example. So let's say that let's say that this is an example of a line segment with length A, and this is an example of a line segment with length B. then you can draw circles around these. Like you can draw a circle around point P with radius A to show, pretend that's a circle, to show all the possible endpoints of line segments of length A starting at P. And similarly, we can draw a circle around Q with radius B. And this shows all the possible, again, pretend this is a circle. This shows all the possible points where this shows all the possible points, all the possible endpoints of a line segment where one of the endpoints is Q and the length of the segment is B. Now, if A plus B is less than or equal to C, then these two circles, either they do not intersect at all. Well, let's just break up the two scenarios. If A plus B is strictly less than C, then we end up with this scenario, where because A plus B is strictly less than C, there is no point on this line segment which has distance at, there's no point on this line segment that has distance at most A from P and distance at most distance at most B from point Q. And this is just because of the fact that A plus B is strictly less than C. And so there is no point which has both distance A from point P and distance B from point Q, and so you cannot form a triangle. If instead we're in a scenario where A plus B equals C, then that would look like this, where this is length A. Pretend this picture is accurate. Okay, so in this scenario, we have A plus B equals C, and so A plus B, there is a single point where these two circles intersect, and it is precisely on the line segment between P and Q. So then the only So that means that there is a point which has both distance A from P and distance B from Q, but this point lies on the line segment from P to Q, and so this is a triangle with zero area, and so we're not considering it. Then the last scenario is one in, can I erase this? Okay, well, whatever. The last scenario is one in which A plus B is greater than C. And then what this will look like is, let's just draw it like this. And this will be B. Then there will be 2 points on the line segment between P and Q. That Okay, so the intersection of this circle, I'll just call it this circle on the left. The intersection of this circle on the left with the line segment between P and Q has a point which is to the right of the intersection of this circle with the same line segment. And then between these 2 points, like if we're thinking a bit of this like on the xy plane, then there is like an x value between these 2 points such that you will get these two, and like if this were drawn accurately, then these 2 points would be lie on like a vertical line, which is perpendicular to the line segment between P and Q. And so we would have 2 points here, which are the intersections of the two circles. And so we can just take one of them, it doesn't matter which, and you could construct a line segment from, and we'll call this point R. And you can construct a point, then the line segment from P to R will be A, and the line segment from R to Q will be B, because of the circles that R lies on. And so then what you have done is you have formed a triangle whose, where the lengths of the sides of the triangle are A, B, and C. And this triangle has an area greater than 0 because A and B do not lie exactly on the line of length C. Okay, and so this geometric argument, and again, these pictures that I've drawn, the actual validity of the arguments, because pictures can be deceiving, the validity of the arguments rely on like geometric theorems and stuff from like, oh, what is that book called? You know, the famous geometry book from, is that literally just the elements? This is really embarrassing to forget this. But yeah, no, these are like famous ancient geometry theorems that are supporting this proof. But basically, using those theorems, you get a proof that indeed, if A plus B is less than or equal to C, then you cannot form a triangle. And if A plus B is greater than C, then you can form a triangle. And so then for this, for our problem here, what we need to do is we need to find, we need to look through all like triples of entries of nums and check if the sum of the smaller two numbers is greater than the value of the largest of the three numbers. And if this is valid, then then that is a triangle, and we need to take that perimeter length and output it. And now this says return the largest perimeter of a triangle with non-zero area. And so what you would have to do here, like just from what we've said already, what you would need to do is go through all possible combinations of three elements of this array nums, and if it forms a triangle, get the perimeter and keep track of it, and then you can sort of like have a running tracker to keep track of like what is the largest perimeter that you've come across so far. And every time you run into a valid triangle, you check if the parameter of that triangle is, if it surpasses the largest perimeter that you've come across already. And if it does, then you just replace it. You replace the largest perimeter that you've come across with the perimeter of the triangle you've just inspected. And then you run through all the examples, and eventually you will have, once you go through all the examples, you will have at some point gone through the triple that gives you the largest triangle, and so you just use that. Now, thinking about this, if we were to implement this, this would be very computationally intensive because you would need to consider every triple, every combination of three elements of the array nums. And so this, the computational complexity would be like big O? I haven't worked with complexity in a while, but yeah, I'm pretty sure it would be like big O of n cubed, or O of n cubed, something like that, where n is the length of nums. So this is like this is like cubic in the length of the array. And this is pretty slow, especially given how large these arrays can be. I guess that this isn't like awful, but still, like we want to come up with ways to avoid this. And so we can think like, is there anything else, like anything clever that we can do to like avoid having to check every possible combination? And so if we think about it, basically we need to check that A plus B is greater than C. And so if we're given a value of C, then we basically want to find the largest. If you're given a fixed value of C, then you want to. Then the only condition is that A plus B be greater than C. So you want to find the largest possible valid values of A and B. And so this might lead. So if you're thinking like, okay, so what would be the largest possible values of A and B be? Well, I am seeing a gap in my proof, so I'm going to pause for a minute while I figure this out. All right, I am back. My AC is going, so I hope that's not creating a lot of background noise. Anyways, first of all, this is the elements by Euclid is what I was thinking of earlier. And the other thing is I had paused to think of a corner case that I had not considered, but I just realized after thinking about that the corner case actually is not a concern. And so we can proceed with the algorithm that we were going to move forward with. And so basically the argument here is, first of all, basically what we're trying to do is we're trying to figure out a way to simplify our algorithm so that we don't need to check every combination of 3 elements of the array. And so let's suppose we have like some array, and we can Python has a really nice sorting algorithm, so we can just assume that the array is sorted in increasing order. And so then let's say we find 3 values that we can make a triangle from, like 3, 4, and 6. Could we make given that we know that this forms a triangle, can we form a larger triangle? Just from knowing that we can form a triangle with these 3 values. And it turns out we can. And the way we do that is we just use these 3. And so we need to check, like, first of all, because basically the logic here is we need A and B. So we need A to be less than or equal to B and B to be less than or equal to C. So all that needs to happen is that the 2 other, so the largest value we choose needs to be fixed, and then the other 2 values just need to be to the left of it in the sequence. And so let's just choose the 2 values just to the left of it. Because what we're trying to do is we're trying to maximize the value, we're trying to maximize the sum of the 2 values with smaller indices. And so the best way to maximize them is to choose the largest indices that we can, because that will give us the largest values that we can. And so of course the largest ones that we could possibly choose would be the ones that are here. Okay, so basically what the argument here is that if you can form if you can form a triangle using 3 values, then you can form a triangle with possibly larger area or possibly larger perimeter by choosing the 2 values just to the left of the largest value. And if this is true, then the largest triangle that you can form is always going to have the form of 3 consecutive values in the sorted sequence. And so then all you need to do is sort the sequence or sort the array and then loop through it once and check each trio of adjacent values. And so let's actually mathematically prove that verbal argument might be sufficient to convince you that this works, but let's actually prove it. Okay, so suppose I and j and k are integers in increasing order are such that there is a triangle with side lengths nums I, nums j, and nums k. Okay, so, but we're also going to suppose nums is sorted, and sorted in increasing order. Okay. Okay. Let's see here. Then, okay, so what about the 2 values, what about the 2 indices before k? So we have nums k minus 2 and nums k minus 1. Can we form a triangle using nums k minus 2, nums k minus 1, and nums k? What we demonstrated up here is that yes, we can. But to prove it, what do we need to check? We need to check that these let's see here. So nums, we need to check that they're in increasing, or that they're increasing, and this is true since nums is sorted. And as for the triangle thing, we need to prove that nums k minus 2 plus nums k minus 1. Let me make this a little nicer. We need to prove that this is greater than c. Well, this is certainly going to be greater than or equal to, well, k minus 2. So since I is strictly less than j is strictly less than k, then the largest possible value of j is k minus 1, and the largest possible value of I is k minus 2. So I is less than or equal to k minus 2, and since nums is sorted, that means that nums I is less than or equal to nums k minus 2. And furthermore, by the same argument, nums j is less than or equal to nums k minus 1. Because, again, j is strictly less than k, so the largest possible value of j is k minus 1. And so that means that j is less than or equal to k minus 1, which means that nums j is less than or equal to nums k minus 1. Okay, and we know since I, j, and k are such that we can form a triangle with nums I, nums k, and nums I, nums j, and nums k, that means that this sum must be strictly greater than nums k. So we can form a triangle with side lengths from these two values. And basically in words, the perimeter is going to be greater than the triangle we started with. And mathematically, if we add these up, it's going to be greater than 2 nums ij. So j I. Okay, so what this means is that for any triangle where the index of the largest value is k, we can form a triangle of possibly greater perimeter from the values at indices k minus 2, k minus 1, and k. And therefore, the largest triangle that you can form from any three values of the array is going to consist of three, we can get we can find this perimeter value just by considering all triples of adjacent indices. And so that's going to be our solution. So let's implement that. So basically we're going to sort the array, and then we're going to loop through all triples. And basically, so how do we want to do this? We want to start, so nums is sorted, and so the largest values are going to be at the end. So we want to check triples of adjacent indices, but we want to start at the very end and work backwards, because we want to find the largest perimeter. And so basically we're going to start with the largest values, and the first time, if we start with the largest values and work down, then as soon as we run into a valid triangle, it's going to be the largest possible perimeter. Because if there were a larger triangle, then it would consist, then we know that it would consist of adjacent indices, and we know it would have to be larger indices, but we already checked those. Okay, so we start it from the right end of the array and work backwards to the left end. And so we're going to loop for I in range, and we're going to track the index of the leftmost of these three indices. Okay, so if we're at the end of the array, the index of the final entry of the array is length of nums minus 1, because indexing starts at 0. So the index of the final element is length of nums minus 1, and then if we want to consider like a trio of indices that ends with that, then the middle one would be index length of nums minus 2, and the first one would be length of nums minus 3. So length of nums minus 3 is where we're going to start. And we want to work all the way down to 0, going backwards. And so we're going to put -1, because again, the -1 here tells us that we're going to be counting down backwards. And when we work with range, we don't include the final value here. And so we want to go up to and including the first index of the array, which is index 0. And so we put -1 here. And then we just need to check if the triangle condition is satisfied. So if the if the value at index I plus the index at I plus 1 is greater than, oh, I should spell this right so that I don't get errors, is greater than nums I plus 2, then this is the triangle with the greatest area. So we return the sum, we return the sum of the three. And so again, with the indexing, we go from I up to I plus 3, because when we index in this way, we do not we include the first index, but we do not include the final one. And we want to include indices I plus 1, and I plus 2. So we go up to I plus 3. And then we're going to return 0. Because if we've gone if we've gone all the way through the array and have not found a triple of adjacent indices that gives us a valid triangle, then there's no triangles that can be formed. And so then we will return 0. Yeah, because if we could form a triangle, because if it were possible to form a triangle anywhere in the array, then again, we could form another triangle using adjacent indices. And if we've checked all of them and not gotten anything, then there are no triangles at all. And so we return 0. Okay, and then we submit this. Great. Okay, cool. Oh, this is interesting. Yeah, this sort of like jumps around sometimes, because I tested this same function out earlier and it performed better. Like it was more like around here. But I guess it's just sort of random. There's some randomness involved with this. But yeah, so this is another one of those exercises where there's like there's a lot of work if you want to prove that your approach is mathematically correct. But the actual problem itself, if you're just like in thinking about it intuitively, you can sort of like come to an answer more quickly, and the code doesn't end up being super complex. What's more complex is the thought process behind generating the code and demonstrating that this is the correct solution. But yeah, that's it for this problem.